Oh. Hello and welcome back to Calculus 3 section 15.6 on tangent planes, linear approximation, and differentials. A whole shopping list of things in here. And what we are doing now, we are going to take those three concepts you know from Calculus 1 and upgrade this into Calculus 3. So into 3D, right? First off, tangent plane. Clearly an upgrade from the tangent line. Now, tangent line was measuring the change on the 2D graph. Tangent plane is going to measure the change in space on a surface. The greatest example of the tangent plane is obviously the graduation cap, all right? Because the little tangent plane is tangent to your head, right? And when you think about it, you have some kind of a surface. So come up with whatever kind of surface you have, and there is going to be a point on that surface. That point is going to have the point, should I call it x0, y0, z0, or abc? Yeah. Let's go with x0, y0, z0 point. And then what happens there is you are going to get the tangent plane at that point, and that tangent plane is going to have the normal vector n, and that normal vector n will be the normal vector of partial derivatives computed at this point. Apparently the point is ABC, so I'm changing x0, y0 into ABC to match the notation in your textbook. The other notation is from the other book. So now this vector n, and this is right, the normal vector, is going to have the partial derivative in respect to x computed at ABC, comma, partial derivative in respect to y computed at ABC. There is a reason why I don't like ABC notation, and I'll explain. And then partial derivative in respect to z computed at ABC. The reason why I don't like this point to be ABC is because I don't want you confusing the ABC point with the old ABC normal vector that we had. Remember that the first time we learned a plane and we said normal vector was ABC, right? So now it's the point is ABC. So it's not consistent. The book is not consistent with the notation. But, you know, such is life. So keep moving. So what do I have over here? Well, I have the normal vector and I have my ABC point, so we know to set up the equation of the plane. If you have a normal vector and you have a point, you can quickly set up equation of the plane. So equation of the tangent plane is given by, in this case, fx computed at ABC times x minus a plus fy computed at ABC, right? Because we are times y minus b. We are at ABC point now. And then plus partial derivative of z calculated ABC times z minus c equal to 0. So this is the equation of the tangent plane. You can see that these guys over here act as a slope, right? And those are partial derivatives, so it makes sense. And then you have centered at the point ABC. So all of the features of the plane are present. So say you have a shape given, let's say, x squared over, you tell me what this is, okay? X squared divided by 64 plus y squared divided by 16 plus, let's say, z squared is equal to 1. What would this be?
It's not an ellipsoid, right?
It is exactly ellipsoid. Because we have radii 8, 4, and 1. Right? 8, 4, and 1. So if I want to find the tangent plane at ABC, so tangent plane at, well, we can actually assign, let's go assign 0, 1, and then we have to calculate z value. So I'm just going to quickly calculate. So 0 will kill x. This is going to be 1 over 16 is equal to 1 over 16. So z squared is equal to 1 minus 1 over 16. And that's going to be z equals square root of 15 over 16, which is plus minus square root of 15 over 4. So square root of 15 over 4. Right, so that's just me quickly calculating. You can't put whatever point, because if it's not on the surface of the, right, you're not going to get tangent plane, yes.
So I'm like bringing everything together correctly. The normal vector is just the gradient of f.
Yes.
Right?
We are going to have a concise, nice vector equation for that, but let's get there. So what I'm going to do now is I'm going to find my partial derivatives, and I'm just going to do this, and I'm going to write here the name, the implicit form. An implicit form for this particular case would be that f of x, y, z is equal to x squared over 64 plus y squared over 16 plus z squared minus 1 equal to 0. So this is the implicit form of the equation you have. You move everything you have to the left side and equal it to 0. So this is what implicit form is. And now that you have implicit form, you find your partial derivatives fx of x, y, z. So to find the fx of x, y, z, you just look at the whole thing over here. It's going to be x over 32. To find fy of x, y, z is going to be y over 8. And to find fz, xyz partial derivative is going to be 2z. So these are our partial derivatives. Now I need them calculated at the point of interest. So fx is equal to 0. Fy is equal to 1 over 8. And fz is equal to root 15 over 2. All of these at 0, 1, root 15 over 4. I need to compute this. Now we plug that all into the formula. So 0 times x minus 0 plus 1 over 8 times y minus 1 plus root 15 over 2 times z minus root 15 over 4 equals to 0. X component dies. You have 1 over 8 y minus 1 plus root 15 over 2 z minus root 15 over 4 equal to 0, and that's your tangent plane. At 0, 1, root 15 over 4. If you change the point, the entire calculation changes to accommodate for the new point. You can. It's just, it's not a big deal, but then you have to calculate extra stuff. So you have 1 over 8 y minus 1 over 8 plus root, disgusting, 15 over 2 z minus 15 over 8 equals to 0. That's 1 over 8 y plus root 15 over 2 z equals, that's equals 2. You can multiply through by 8 to make it even nicer. So now it's y plus 4 root 15 z equals to 16. Right? Whatever makes you happy. Remember, right? This is a calculus course. Your happiness is our primary concern.
On the example, we need to distribute it, or does not matter?
Does not matter. If you have time, go ahead. I mean, you would clearly want to program this because it has less operations. That's how you make your software more efficient. It's not just faster hardware, it's also more efficient software programming, which means less mathematical operations for processor to work on. Now, tangent plane for z equals f of xy. This is explicit form. And that one will be given as z equals fxab times x minus a plus fy ab times y minus b plus f of ab. So these are two different cases. I'm just gonna, I'll just put note. If I have, let's say, ellipsoid, equation is x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. Should write this in blood, but not a function. So we use implicit. But if you have of z equals x squared over a squared plus y squared over b squared, It's a function. So we can use explicit. Can you use implicit? Yes. But you're not using sledgehammer if you need to put a painting in a wall, right? The little nail. Use a framing hammer, right? It's easier to lift than a 50-pound sledgehammer.
Sledgehammer is more fun than.
Yes, which is why implicit function is more fun because it has more calculations and it's right. So 100% of what you said is correct, and I agree. So we have these two formulas which calculate the equation of the plane, which is tangent to the surface at the point you're interested in. This concept is about 250 years old, maybe even older. So at that time, to everyone's surprise, they did not have calculators and computers. My son has no concept of that. He's playing Minecraft and he asked me, "Daddy, did you play Minecraft when you were a kid?" I said, "No. Dinosaurs used to walk around when I was a kid." All right? Or so the creationist thing. Anyway, so what I have in the in this situation here is, if I have no calculator and I need to compute a point that has a square root or something, it's much easier to work on a tangent plane on a point that it's close by and then compute in the tangent plane rather than in original function we had either ln or square root or something like that. So let me give you a Calculus 1 flashback over here, and then we'll do the same thing in Calc 3. So Calc 1, linear approximation. So say that we want to calculate in Calc 1 square root of 82. All right, so what we know is that we can figure out square root of 81 and find the tangent line at 81, which means that at 82 the y value, so at x equals 82, the y value from f of 82 and y value from tangent line computed at 82 are very close, which is why it's called approximation. They're not the same, but they're very close. So if I am to compute this, I would figure out the tangent line, and then I would compute 82 in the tangent line rather than computing 82 in the square root. So if I find the tangent line over here, we did have that linearization formula for fast calculation, which was given by this formula, if anyone remembers it. And in our case, our A was 81 because that was the easy one to compute in a square root. So we first find the equation. So that's going to be f of 81 plus the derivative at 81 times x minus 81. Our function for this problem was square root of x, and our f prime is 1 over 2 at x when you take the derivative. So now my L of x is square root of 81 plus 1 over 2 times square root of 81 times x minus 81. So calc 1. L of x is equal to 9 minus 1 over 18 times x minus 81. This is the tangent line. So square root of 82 is approximately equal to L of 82. So now I need to calculate this, which is 9 minus 1 over... Why minus? It's a plus. Holy nightmare. Plus, there we go, 1 over 18, and then I have 82 minus 81, which is 9 and 1 over 18. So calculator will give us that 1 divided by 18, I mean, you do this with a stick in a sand and so on, is, so this is approximately 9.0555, and I'll put 6, okay? Calculator for square root of 82 will give us approximately 9.05539. They match for the first 3 decimal places, right? This is how crazy good these approximations are. But today we have calculators and computers, so it's easier to just punch in square root of 82 in the calculator or the computer and get the value rather than do all of these calculations, so you avoid using calculator, right? So all of this stuff that we are learning is completely obsolete in today's time, but it's kind of cool to know because, you know, someone might eventually tell you, what do you know? You bring this up. They will have no arguments. I'll promise you that. All right? Also, this is really cool for Thanksgiving dinner. If you have a family over or something, right? Hey, Nick, what's new? Here, let's work out the tangent plane. It's like a cool concept we just worked. So now we hopefully remember the concept of linear approximation. Your job is to find the close point to the point of interest, right? Find the close point that actually works in your calculation, and then develop a tangent line at that point, and then calculate the point of interest in the tangent line rather than the original function. Well, now that we shift for Calc 3, so back to Calc 3, we approximate in tangent planes. So we will use tangent plane to approximate the value. So tangent plane. So now our formulas that we had before for tangent planes are just going to be recast with those L's. So the explicit one first, L of x, y, will be our fx, ab, x minus a, plus fy, computed at ab, times y minus b, plus f of ab. And if you take a look at this formula, it's identical to your linearization formula in Calc 1, because you had L of x equals to f of a plus f prime of a x minus a. Well, now you are in 2 dimensions, so you also have a y term for the derivative, right? But the single f of a is a single f of a b. Yeah, they're in a little bit different order, but it's addition, so it's commutative. So I hope you can draw the parallel between Calc 1 formula and the Calc 3 formula. It's the same thing, except you are adding another dimension because you have one more dimension to deal with. But these two terms are technically the terms. If you drop out the b's, it's exactly what you have in Calc 1. So that's the explicit form, and then you have the implicit form, where Lxy is going to be the one with the capital F. So it's fx at ABC, x minus a, plus fy ABC with the y minus b, plus fz, kill me now, ABC z minus c, plus f of ABC, and these would be your linearization formulas in Calc 3. So now let's get a nice example to work this out. What is this going to calculate? This is going to calculate to approximate the value of something that you're trying to compute.
Shouldn't the second equation be L of x, y, z?
Yes, it should. And I will add z into the second equation because it is a L of x, y, z. I was just testing you to see if you're paying attention, and very good, very good.
Extra points on the exam.
This was not exam. I'll make sure to notice all of the points on the exam. The gap is annoying, so I close the gap. All right, so a problem, right? That's why we all gathered here in such a large number. About 10,000 students present at this lecture. They're just very quiet. Uh, 37 looks wonderful because it does have ln in it and all of this stuff. So let's take a look at 37. Probably I'm going to regret this, but f of x, y, z is given as ln of 1 plus x plus y plus 2z. Cross your z's. So ln of 1 plus x plus y plus 2z. And they would like to compute, well, approximate f at 0.1.
Is it 2z or
2z.
z's?
2 times z. So 0.1, negative 0.2, and 0.2. So this is what's given. You have a function, and you are supposed century. Or we can just run through tangent plane approximation because we can, right? So we all know that the derivative of ln is you control C, control V on the denominator. And then you take the derivative of the one you need, which is x, so that's just going to be 1. Then fy, again, control V, control C, control V, there we go. The derivative of y, it's also going to be 1. And then finally, partial derivative in respect to z is going to be 2 over 1 plus x plus y plus 2z. I have my partial derivatives. Now I am supposed to pick my point where I'm going to approximate stuff. Well, the best point 0, 0, 0, these are your ABCs for your calculation. So now, fx at 0, 0, 0 is 1. Fy at 0, 0, 0 is 1. And fz at 0, 0, 0 is 2. To find your linear approximation Lx, Lxyz, you will go 1, x minus 0, plus 1, y minus 0, plus 2, z minus 0, and your, plus f of 0, 0, 0. F of 0, 0, 0 is going to be what? ln of 1, which is 0. So linearization of x, y, z is going to be x plus y plus 2z and then plus 0. So now, what is f of, what the hell did they have over there? 0 point something, 0.1, negative 0.2, and 0.2 is approximately equal to L of 0.1, negative 0.2, 0.2, which is 0.1 minus 0.2 plus 2 times 0.2, and that gives us 0.4 minus 0.3. So if I am to compute in the calculator the ln of these values, I should get 0.3. So let's go check over here. Ln of 1 plus 0.1 minus 0.2 plus 0.4. So these are our calculations. We need to find ln of, what do I have? 0.5, 0.3 is 1.3. Yeah, 4 minus 20. Okay, so now what do we get for ln of 1.3? We get 0.26. We're 4 cents off. We're good to go, right? It was a third-dimensional calculation too, so you have 3 degrees of error coming in, and we are only 4 cents off. Hey, it's great. With linear approximation, whether it's a tangent line or a tangent plane, we are able to approximate the value of the function by doing all this extra work for no reason to check off.
Question.
Yes?
Is it still called linear approximation, or is it like planar approximation?
Linear because the plane is the linear concept because x and y and z are all on the first power.
Oh, okay.
The time when I really facepalm is when I read exam 2 on Calc 1, and I say find the equation of the plane, find the equation of the line, and someone says, oh yeah, y equals 3x squared plus. I go, whoa, what? Or 1 over x or something like that. So linear in mathematics doesn't just mean linear line. Linear in mathematics across the board means that it's not squared, it's not square rooted, it's not sine of something. So linearity is the feature when you have a variable raised to the first power. And that can be x, y, z, all of them added together. So a plane is actually a linear concept because all of the powers are 1. The last part of this lecture are differentials. So and if you haven't picked up the difference from Calc 1, I will repeat. Differentials are approximating the change. Linear approximations approximate the values. Differentials approximate change. So if you want to calculate square root of 99, you will use a linear approximation to figure out, right, and a equals 100, to figure out the tangent line, and then you will use your 99 in the tangent line. You are approximating the value. You are approximating square root of 99. Differentials approximate the change between square root of 100 and square root of 99. Right? So, for instance, when you go to bed, your joints relax and your body relaxes, and when you wake up in the morning, you are tallest for the day. Tallest. As you move through the day, walking, your upper body weight compresses on the joints slightly, and by the end of the day, you are tiny bit shorter than when you woke up in the morning. So the tallest for the day, when you wake up, the shortest for the day, right before you go to bed. During the night, your joints expand a little bit. These are fractions of an inch, but they're there. So, and that happens over time. Everything happens over time, which is why our derivatives are divided by dt. So now we can measure the change between the height in the morning and in the evening, which is why for kids it's so damn important to sleep so they can grow, because you don't get to grow too much during the day as a kid, because again, you're running, well, you do the same thing. You find derivatives, and derivatives are approximating the change. So, going back to Calc 1, you say y is equal to f prime of x. When you differentiate that, you get dy dx equals f prime of x. Oh my god. Y is equal to f of x. Sorry. Y is equal to f of x. That's pre-calculus. And then when you differentiate, you get that dy dx is equal to f prime of x. And then you move dx to the other side, you get that the dy is f prime of x dx. Now, delta x, which is the change in x, is the same as dx, and delta y, which is what you are interested in, is approximately, not the same, but approximately equal to dy. So, we can actually define in Calculus 1 formula for differentials where the true change, which is unusually annoying to compute, is going to be approximated by the differential dy, and differential dy is exactly equal to f prime of x times delta x. Now this delta x over here is simply x2 minus x1 new minus old value. So, if I am inflating a spherical balloon for a party, if I add a little bit of air in the balloon, the radius grows, and the surface area of the balloon grows, and the volume of the balloon grows. So if I So this was a Calc 1, right? So if I have a balloon, spherical balloon, we have that the volume is 4/3 pi r cubed. And I want to calculate delta V. Well, we are in the 21st century. You just plug it in a computer, you get exactly V2 minus V1. You do not actually have to compute these things by hand, right? See, the trick is that the radius of the balloon was, let's say, I don't know, it's a large balloon. So let's say the radius was 1 foot. How about 1 meter? Radius of the balloon is, wow, 1 meter. That balloon is as tall as I am. I don't care, 1 meter, whatever. And then it changes to 1.1 meter. Well, this means that you have to plug in 1 over here, compute everything to get V1. That's the old. And then plug in 1.1 and cube it to calculate V2, and then you subtract. That's how you get the exact change. But the differentials say, let's not do that. Because we can say that change in volume is approximated by differential, right, of dV, which is simply the derivative of this, which is 4 pi r squared, and then times dr. And dr is simply 1.1 minus 1, new minus old, which is 0.1. So now your dV is approximated, delta V is approximated by dV, which is 4 times pi times 1 squared times 0.1 squared, which is 0.4 pi, approximately 1.2 meters squared. So by expanding the radius of the balloon by 0.1, approximately expands the volume of the balloon by 1.2. Oh, this is a volume cubed. Holy nightmare. This is the second time I messed up on a volume in a cube today. So that was Calc 1. What do we have for Calc 3? We just have another dimension. So we just add that into the mix of our differential equation. So back to Calc 3. Differential. So definition over here. I'll just put the delta z is approximated by dz, and that's equal to fx xy times dx plus fy xy dy. Formula is identical. Here is your f prime dx, and then we just had to add another dimension for y because it changes in two ways. So let's take a look at the example from the homework. By the way, what if this was w as a function of x, y, z? How would you modify this formula?
Just add this in.
Yes, you will have delta W, dW, and then you will have plus Fz. And you can, if you want to work in 15 dimensions, you still can. All of these, just scale up. They have all of these cute problems. There is a few application problems with two-dimensional input, and then two problems with a third-dimensional input, which is a 4D problem, and then five-dimensional problems as well for you to enjoy for differentials. Changes in the volume of a cone. That's a nice problem, 43. So the volume of the cone, since it's a spiky object, it's 1/3. Base is the circle, so pi r squared times the height. That's the volume of the cone. And please note that we do have radius and the height. So that's the two input variables, and v is the third variable. So you have technically, x, y, and z situation here. The change in volume is going to be approximated by the differential dv, and that one is equal to, now what are my variables? My variables, you know what, I'm going to rewrite this formula for volume one more time, because I want to have it as clean as possible. V equals pi over 3 r squared h. The reason why I'm just forcing this together is just to emphasize this pi over 3 is a constant, right? So we don't have to worry about 1/3 and a pi separately. It's just all on a pile. So I need to take the partial derivative in respect to r. That's the first part. So I have 2 pi over 3 r h, and then it's dr. Plus, and now I need partial derivative in respect to h, which is pi over 3 r squared, and then derivative of h is 1, and then I have the h. Now, delta v is approximated by dv, and dv is 2 pi over 3 rh, and I'll put this as delta r, plus pi over 3 r squared delta h. So in this problem, it says that the radius grew from 6.5 to 6.6, and the height the height decreased from 4.20 down to 4.15. So my delta r is 6.6 minus 6.5, new minus old, is equal to 0.1. My delta h is 4.15 minus 4.20, again new minus old, is negative 0.05. Now I have to plug these in the formula. So delta v approximated with dv is 2 pi over 3. R is 6.5, use old values. 6.5, h is 4.2, and then I have dr, which is 0.1, plus pi over 3. I have r squared, which is 6.5 squared, times negative 0.05. So delta v is approximately dv is approximately equal to a number. This is going to approximate by how much the volume changed. It's not approximating the value. At some point in time, it approximates the change that happened over time as the radius grew and the height shrunk for this particular cone. That's it. I hope you're not disappointed. Bye.